Hi, my name is Joe Chacon. I'm an electrical engineer with Padge LLC. This is the 7th of several videos about harmonics. Today, I want to talk about active harmonic filters. These are my favorite devices for mitigating harmonics, and I trust you'll see why. Let's get started. Let's first define active and passive. We have only looked at passive harmonic and power quality mitigation devices in previous videos. By passive, I mean an inductor, a capacitor, a resistor, or some combination of these devices. Modern active harmonic devices use a switching device to control harmonics. The switching device is almost always an IGBT. An IGBT is an insulated gate bipolar transistor. They are practically an ideal device for higher voltages and currents. I'm not going to go into any more detail about IGBTs except to say they are active devices because they require a gate driver to gate them on and off. I don't design active harmonic filters for a living. I do help with specifying them though. I have drawn an example circuit of what one would look like. This is called an H-bridge. The IGBTs can gate themselves in such a way as to whether they are charging the DC link called sinking or discharging it called sourcing. The far left of this schematic is the DC link. There is a fair amount of capacitance on the link to keep it charged. The yellow line here shows an example of sinking with S4 and S3 gated on. The red line shows an example of sourcing with S1 and S6 gated on. Again, sinking is charging the DC link and sourcing is discharging it. These switches happen extremely fast. I'm talking about 4 kilohertz up to 20 kilohertz. That's 50 microseconds up to 250 microseconds. Fast, right? You can have these combinations of switching. The gate driver is working fast to constantly decide to sink or source based off some current transformers and voltage-sensitive devices placed where you want to mitigate harmonics. The net effect is a real-time response to provide compensation current injections that, in theory, can completely neutralize the harmonic content of a system. Newton discovered the third law of motion. That applies for active harmonic filters too. Newton said, for every action or force, there is an equal and opposite reaction of force. So, if the active harmonic filter is seeing 5 amps on the 5th harmonic, it will inject 5 amps of canceling current at 5 times 60 hertz or 300 hertz to cancel it. How do you cancel AC sinusoidal current? You do it 180 degrees out of phase. Let me show you this plot. The blue line represents the 5 amps of harmonic content the active harmonic filter sees. The orange line represents the canceling current it injects to correct it. I hope you can see when you add these two, it is like adding 1 plus -1. They cancel out. Rudolf Clausius and Lord Kelvin told us in the first law of thermodynamics that energy is neither created nor destroyed, only transferred from one form to another. This also applies to active harmonic filters. When the active filter needs to charge the DC link, and when it provides the compensation current, here it does. Basically, it doesn't pull current from out of nowhere. It's constantly charging and constantly discharging the DC link, obeying the first law of thermodynamics. Active harmonic filters are sized based off voltage and current. They will usually specify how many harmonics they can cancel out. The ones that I have specified in the past come in increments of 50 amps. That is 50 amps, 100 amps, 150 amps, and 200 amps. If you need more compensation current, then you can usually parallel them. I usually size them with power system analysis software. The one I happen to use is called Easy Power. There are others out there. The Harmonics packages of power analysis software can be quite expensive, but worth it if you have to size active harmonic filters quite often. I plan to make a video later showing how I use the harmonic package within EasyPower. I hope it translates over well to packages like ETAP and SKM. I plan to show you how I calculate compensation current on that video. I like active harmonic filters for two reasons. The first reason is they can also provide power factor correction. If you're procuring one that doesn't provide power factor correction, then buy one that does. That can be a game changer if the utility is hitting you hard for excessive power factor. The second reason I like them is they are perfect for an existing system that has a lot of harmonic issues. An existing system usually has deeply embedded hardware over a massive amount of square footage. It might be unfeasible to go to specific places within that system and put in multiple passive devices. It is probably feasible, though, to put an active harmonic filter as close as possible to the point of common coupling, and the majority of the harmonic issues go away, especially at the point of common coupling. I hope it is a bit clearer as to how harmonics can be mitigated by active harmonic filters. I hope this knowledge can help you become the harmonics guru in your company. Please look us up at padge.org. That's PADGE.org if you need anything on this topic or others.